Hello, everyone. I hope you're having a lovely, lovely day. Welcome to the lecture Knowledge Discovery. Particularly today, we'll be having a look at text mining. My name is Christian Nuli, and let's get started. Where in the semester are we at now? You started in October, right? There was some introduction, some organizational stuff that we talked about back then. You've seen what it means to design experiments. You've heard a lecture on neural networks and deep learning, as well as seen some graph neural network stuff. Just last week, you saw explainable AI, and now comes the block with text mining, followed later on by large language models. So a brief overview of what we'll have a look in this block. Well, we'll start with the motivation. We'll see, what documents in text mining actually are. Then we'll see how to represent these documents, among others, as word representations, and how to encode these in different ways. And then we'll move to actually showing what kinds of tasks you can complete or you can try to tackle with different kinds of representations that we'll be seeing. Among others, there will be stuff like entity linking or named entity recognition, which are pretty popular within the natural language processing space. So, the title of the lecture, Knowledge Discovery. I hope you know it. You've seen some graph neural networks, and we'll have some language models later on. And now we're kind of building the foundational blocks for that, I guess, for the future lectures. And specifically, what we'll be having a look at today will be the art of deriving findings from text data, with the text aspect bolded for today. What kinds of text findings are there and what kind of tasks exist? There's sentiment analysis, for instance, which tries to discover what kind of sentiment is someone expressing in a piece of text, in some kind of passage. We can also classify text into all kinds of categories that we define ourselves. Among others, you can also see sentiment analysis or sentiment classification as a text classification task where we just define different moods someone is in. We can cluster our text, which sounds a bit difficult. If you just take words, how do you cluster them together based on what parameters or what kind of features do you want to cluster? You can figure out what kind of models are contained within a text or are being talked about. There's named entity recognition, which tries to figure out what kind of entities can we find in a specified text. And then entity disambiguation, entity linking, we'll get into it a bit further, but there's also tasks which are closer to what you know from search engines, like information retrieval along with search, summarization, and then bias detection. Mitigation is another thing you can do. You might also want to translate from one language to another, or you might just want for your model to actually try to understand natural language the way it appears. So, as you may have guessed, most of these tasks nowadays, you do it with machine learning. And we design different kinds of experiments on or training schemes, architectures to resolve these tasks or to tackle these tasks, and we apply machine learning algorithms to them. Well, that also means that includes loads of linear algebra and, other kinds of maths as well. So, we have a figure representing a sample machine learning pipeline. We start with the data. that we then feed to the model, and then the model will want to evaluate it afterwards. Different kinds of tasks we might have to do with data include, well, we need to collect the data somehow. We might download an existing data set. We might crawl data ourselves, extract the parts that we find relevant for our tasks, clean it, remove all kinds of noise or things we don't need from it, like unexpected characters. We might have to prepare the data in different ways to load it into a specific data structure to make it easier for processing later on or to make it more efficient. We might want to analyze the data so we know what we're working with here, to see if our preconceived notions or our intuitions actually fit what we want the data to be like. So it's really useful to actually analyze your data and to have a look at it and see what's actually in it. Then you use the data to train a model. But for the model, you also have to select the proper model, then potentially do some feature engineering, which, depending what you do, you don't really specifically engineer features, but you just throw everything at it, in quotation marks. You then train the model based on the data, and in the end, you might want to do some hyperparameter optimization as to get like better results. For the evaluation, well, you also might want to deploy, monitor, and maintain it. But today we'll have mostly a look at, well, at least we'll start by taking a closer look at the data. So for text mining, what is our data? There's different kinds of large language models out there. Just name a few like Claude, Gemini, and the ChatGPT models. And yeah, they're all the rage nowadays. And they have to get their data somehow. They have to work on data, and what is that like? The data for these kinds of models tends to be text documents in all different kinds of forms. As we saw before, like on a previous slide, those were screenshots from websites. A document can be an entry on a website. It can be an article. It can be unstructured plain text, or it can be partially structured, like what we saw with the news websites, where you already know, okay, there's a header 2. A header 2 means it's a title, or header 1, whichever. And we can then have already a certain degree of structure, because from the title, you might already know what is within an article, or it might have some thought-provoking questions or comments on what is to come. And so there we have kind of a structure, which we can extract with crawlers and then looking at specific HTML tags and then filtering those out and so on. Or when you're working with tweets, for instance, you know that tweets always have a specific length. So based on the length, you can make some assumptions. And yeah, our data can also be noisy, and might not fit exactly what we need. And yeah, all of this here, like whether it's unstructured or partially structured data, it's hard for machines to really understand, to really, in quotation marks, know what it's about, particularly without context. There's all kinds of different contexts. For instance, there's a temporal context where based on what year it is, you might know what the main happenings of the year are. Like if it's 2024, 2025, it's likely something different than in 1924 or like 200 years ago, or what may have it. Depending on the situation, you might also mean something different, and that can also be very relevant. For instance, let's say you're at the grocer's and you're talking about apple, then you're probably talking about a fruit. If you're at some kind of Genius bar and talking about an apple, it's less likely for you to talk about the edible kind of apple. Well, yeah, or you might not necessarily want to take a bite out of it. There might be a locational one, which, okay, that kind of works in the same fashion as where are you at? Like, are you at a grocer's or are you at some kind of electronics store? Political and so on. There's all kinds of different aspects that contribute to context. And the goal for us in text mining is that we want to generate findings as to, well, to hopefully understand the data, want to filter some data potentially to reduce information overload, because we as humans are not good at skimming through large amounts of data, or at least not large amounts of text data at a time. So we'd rather have machines reduce that for us, as we have it for search engines. So rather than going through billions and billions of documents, we have search engines giving us what's actually relevant for us, so we don't have to scan through everything with our eyes and read it and understand it first before, well, getting what we're actually looking for. So we also want to potentially structure our data, because if we structure our data, it becomes easier to deduce something in the future. We can, especially if we can synthesize that knowledge in some kind of data structure, some kind of format, so that we can have a better look at it later on to know what it's about. That'd be really cool. Right. As I alluded to before, we like using machine learning for it. So in machine learning, what we like is a lot of data. Ideally, it would be high quality data. And, well, we also like math, particularly the linear algebra kind. And we also like to have data to use fun math on. So the challenges we tend to face in this regard is, okay, how could we actually apply math to text? Because text is text and math uses numbers. So how could we work with that? We also have an issue, namely that text length tends to be variable. Like if you take tweets, you can say, hey, it's always at most this many characters, and then process them as such. But most of the internet or most of the text data we have is not like that. So dimensions and the length kind of tends to vary. Word order tends to imply meaning. So if we just have a look of what words are in a sentence, that's already a good starting point. But we might also want to know in what order we said them. For instance, if there's we're saying yes to something, but no to something else. Yes, I would like a banana. No, I would not want an apple. If we don't know about the word order, we wouldn't know what we affirmed and what we denied, or what we wanted and what we didn't want in that case. So another challenge is, for instance, that there are words that we might not know. So we tend to have a vocabulary of words that we have worked on, that we might have trained a model on. But what happens if there's new words we haven't seen, something completely new from a different language that we have not trained with? And how to handle that. So the solution to some of these challenges is that we want text representations with fixed length vectors, regardless of the length of the input. And basically, we want to reduce the dimensions from the written language to vectors. Because with vectors, we can potentially do math, like vectors with numbers in them, of course, that we can then apply some linear algebra to, because that's fun and things that we like to do. So